So, welcome to today's class. We are going just to do the analysis and practical side of the analysis that was done last week. Last week we failed to have a lesson, so today we will concentrate on doing some t-taste. I hope Kondowe did all of what was supposed to be done. And so we are going to do some t-taste on the dataset called baby. I shared this dataset on the WhatsApp, as well as for some that provided their emails, I sent this dataset via email. So I hope you have this script already. I will just make sure that we import the data. And there we go. I'll just run the whole script up to the end, and then we can import today's data set. So since this data is a CSV file, we are going just to use the command read CSV, and then we get the data set into the system. So let's see, it's still processing. And there we go. So if I scroll down here, I find that this is a data set that has about 136 observations. It includes the number of the ID. Parity is how many times the woman has given birth. So some up to 8, others up to 6. And the age of the woman, whether the woman smoke or not, whether the woman has a chronic condition, for example, has diabetes or not, and if she has any gestation illness, that's from which gestation week is the woman. So some had to go up to 39, up to 41. Then these were labor hours, the fetal hours, then the mode of delivery. So, and then this is the gender of the baby that was born, and then the weight of the baby, the birth weight, and then the weight of the baby at discharge. So this is the data set, but our concentration will only be on performing t-test. So just like from the lesson, we learned that one sample t-test is when you are comparing a certain value to a value that is in the population. For example, it is in the literature. So that will be our first thing. So we need to do a one sample t-test. And this one we do, I think we did this one at some point in time. So t-test, then I need to get the data code babies that I've already inputted. And then someone says, well, the age of the women is, he makes a claim, and this claim is what we call the null hypothesis. And then the alternative hypothesis is the counterclaim. So like from the last time we ran on t-test. So the claim is that the age of the women is maybe say 20. Okay, so it means that we have gotten this from the literature. Now you want to test that from the data set that you have. Does it apply from what you have gotten from the literature? So you just need to write mu equal to 20. So if you do that, you run that, then you get a one sample t-test. So with the data set, then the t-test statistic, and the degrees of freedom, and then the p-value. And here the p-value is much, much smaller. So the alternative hypothesis that the true mean is not equal to 20. And then you get 95% confidence interval as well as a sample estimate of the value x. So what does this p-value tell us? So since it is much, much smaller, it means we reject our null hypothesis that the mean age is equal to 20, and therefore conclude that the mean age is not equal to 20. Now, if we do the same, for say, for example, someone claims to say, well, what if we say from the literature it says that the mean test is equal to 30, for example. So I will do the same t-test, and then I'll do babies. That's my data set. And I'll pick the very same age. And then I'll say mu is equal to 30, for example. And then if I run this, now you find that the p-value is large. So once the p-value is large, it means we fail to reject our null hypothesis. Therefore, we will conclude that the true mean is equal to 20. So from here, maybe I should put our H naught. So the H naught is the null hypothesis. So we'll say I'll put it in the form of a comment. So H naught, the mean age of women is equal to 20, like in the first place. And then the alternative, which is represented as H1, say the mean or the true mean age of women is not equal to 20. So when I learned this one, in the first place, we find a p-value which is much, much smaller. If the p-value is much, much smaller, it means we reject the null hypothesis and conclude that the alternative hypothesis is true. However, if we do the same, but now we change this one equal to 30, for example, or 35. I'll put 35 and then 35. 30, sorry, I start with 30 and then demonstrate with 35. So I start with 30, and then I run this t-test down here, and I find that the p-value is more than 0.05. Therefore, I will say that I'll fail to reject my null hypothesis and conclude that the mean age of women is equivalent to 30 statistically. So how about if I put 35, for example? So 35 here, I also get a p-value, which is much, much smaller. Therefore, I will reject my null hypothesis and conclude that the alternative hypothesis is true. So this is about a one sample t-test. Similarly, last time we also, from the lecture that Fishani presented, we also learned that there is what is known as independent sample test. So we are going also to demonstrate on how to perform t-test. So it tests for two independent samples. So for example, she demonstrated in there, in the lesson that she presented on the admissions, like whether one is going for bachelor's of law, bachelor of science, and the like, and against the gender. Does gender have influence over what enrollment you are going to do with the university, for example? So in this context as well, we can try to learn to say, okay, does gender, for example, play a role in birth weight at birth? So for example, there is a variable called birth weight, which was captured. Does it differ from males and females at birth? So males and females, these are not related. As such, we cannot term them to say that they are paired, for example. So these are two independent samples. That means male are treated separate from females. Okay, so we can do the same. The best way is to group the data set, but it not necessarily matter, but you can just be sure. So if you remember where we have been using this pipe for so long, so we get to group this one by, okay, we group it by the data called gender. So we do that, and then it flags out something here, don't worry. And then we perform a t-test. But even if you don't group, it still gives you the same. So you perform a t-test of what? Your data set is babies, and then you are interested to check the birth weight. If the birth weight differs on what? If it differs by gender. So if the birth weight differs by gender, for example. So how you do that? And then here comes a problem, and this problem should go. Okay, so if you do that, then it gives you here a two sample t-test. So two sample t-test in this context is independent one. And you see, it says the true difference is mean is not equal to 0. And then what value do we get here? So the value here we get 0.09. Now, from a threshold of 0.05, it means that we are above that threshold of 0.05. And therefore, this value is bigger, or is bigger compared to 0.05. And as I said, if it's bigger than 0.05, then what do you do? So if it's bigger than 0.05, then you fail to reject the H0 or the null hypothesis. And the null hypothesis here was that the true difference in means is equal to, like in one group, for example, in males is equal to in females. While the alternative was saying that the difference in means in those two groups is equal to, is not equal to 0. So maybe I can just write the null hypothesis and the alternative hypothesis so that it should make sense with the explanation that I'm providing. So here it will be the true difference in means, okay? True difference in means difference in means of birth weight, birth weight so this one will be equal to, or we should put equal to 0. what does this mean? This can be written also as, you can write this one as, okay, as if you want to do the gender, so the mean, you say the mean difference, or in short, the mean birth weight in male is equal to the mean birth weight in female. So the mean birth weight in males is equal to the mean weight in females. Or you can put this to the mean birth weight in males minus, it's all the same. You can write it in different ways. And minus that of males is equal to 0. Birth weight, not right, birth weight. Yeah, so, and that's for that. Therefore, it means the alternative will be the same, but you say this one is not equal to 0. So here it will be not equal to 0. That is birth weight in males minus that one. So here it can be not equal to 0, or it can be less than 0, or it can be greater than 0. So that's how we write the alternative. And then there is also in the data set, there is the birth weight of the baby. So that's upon the baby is delivered. And then weight at discharge. So consider this scenario as a scenario, for example, you are doing a research in the development world. Now you have collected, for example, you have collected information in the baseline, and then you implement your project, and then at the end of the baseline, at the end of the project, you want to evaluate your project. So this is one where you can tell whether your project that you've been working on has a significant impact on a certain variable. So here I'll just demonstrate it. Might not make sense, but for example, if it makes sense that there is an intervention that is given to a child. Once a child is born, they record the birth weight of the child. And maybe 2-3 days, if at all there is intervention, but it would make sense for maybe projects. It would make sense for projects that are maybe done, for example, school feeding project would be a good example. So you have gotten scores for your children, and then you distribute maybe food packages to children in order to improve maybe their scores, for example. So you assume to say, well, maybe my intervention, which is to do with the distribution of food, has an impact on the children performance. And if they have any contribution to the children performance, that means after maybe like next year, you still give them. After next year, then you get to you let them also take the test and then compare the results. So you compare the situation before and you compare the situation after, and see if it is statistically significant. Then you say, well, my intervention had an impact. If it's not, then it did not maybe yield any impact. There might be many other reasons why it did not yield any impact. So I will demonstrate with these two how to perform a paired why it is called paired sample, it's the very same people that you are treating now. In here, it's the very same people that were born with a weight of, children were born and then they just took weight after discharge. So I'll go to here and then I'll do a t-test. But this one, t-test for paired sample. So as I said, I'll do a t-test of the babies, but I'll take birth weight at delivery and birth weight at delivery as well as birth weight at discharge. So if I do this, then I run this one. Okay. So here it will bring back the same, like the one that was before. Okay. And because I did not specify here, you would realize that this formula is not much different with this formula. But then here I need to tell this one to say, well, these are from a paired sample. So I need to specify paired equal to true. If I do that, so here, for example, I find my p-value to be much, much, much smaller. So here I'll conclude to say that at least whatever they did to the babies during delivery up to the time they were discharged had a significant impact. So maybe we would consider it that while a child was just born, they captured the birth weight, then the child was not forced rather, but they told the mother to breastfeed the child. We expect an instant weight gain of the child because the child now is feeding maybe the milk directly. So we would take that one as sort of an intervention. So a situation before it was at delivery and the situation after is at discharge, and then we try to compare and if it makes sense. So if it does make sense, here you can conclude to say that it was significant. It's not much different the way we write the hypothesis from the independent test to this sample or this paired t-test. And then from last time, we also learned that you can do the comparison, but maybe for up to 2 or 3 groups. In here, we were only comparing the baby's weight on gender, which is what? A gender is either male or female. Okay, so how about if it's 3? And so from the lesson that we learned last time is that then the t-test become analysis of variance or ANOVA. So I'll also demonstrate on how to construct an ANOVA test, but I hope this one has gotten to you guys because this one is more important, especially in the development world. If you work as monitoring and evaluation, or in the area of monitoring and evaluation, you can be asked to evaluate a project. The most important would be to have baseline value. That's why many other times when the project is initiated, they will mostly request, let's do a baseline survey. So the reason of doing a baseline survey is to get the initial benchmarks. And once you implement the project, of course, there are certain assumptions that needs to be worked out. For example, it's not only your project. I mean, there are other developmental partners, for example, in the working together with you, for example, in the district. So you wouldn't necessarily attribute the success only to your program or the difference only to your program, but at least that's what is being done. So you have the baseline surveys. In this context, our baseline survey was the birth weight, that is the weight of the child at birth, and then the evaluation survey would give us the weight at discharge. So in whatever project you're doing, then this would be important. Regardless that you might not interview the very same people at baseline and at end line, because maybe you might find that you go and then you find that they have relocated from the area and the like, but at least you know that you have a baseline value and you can get the end line value or the end line survey to give you values and then do the t-test and then say, well, our project that implemented at least had an effect on the ground because there was change in what we initially get and what we have found. So if you are testing in more than 3, for example, here we go to a mode of delivery like in here. For example, if I do table and then I just get table of babies, then mode of delivery. So there are several. Others had normal delivery, maybe others had cesarean, or others they used it was sort of an emergency or something. They used lots of methods. So for example, if you have these values, now you want to compare to say, okay, does birth weight differ or does weight at discharge differ from those that were born normally and those that were born maybe through Caesar or something? So what do you do in that context? You need to perform an ANOVA test. So to do an ANOVA test, you can do several ways, but a simple one is to use a function called AOV, analysis of variance. So this one will give you a test results. So perform, I'm trying just to give comments for those that maybe are not with us today. Perform analysis of variance, which is popularly known as ANOVA. So ANOVA is more of a t-test, but it's an advanced t-test because for gender here, we only, I'm just doing this one, and we only had either male and female. So that's why here we did 2 independent sample t-tests. But how about if it's 3 or 4 or 5? You want to compare, like here we are comparing birth weight among boys and among girls. How about if you are comparing birth weight among a variable that has 3 or more? And in that context, you use analysis of variance. The null hypothesis and the alternative hypothesis will be pretty much the same. So as I said, I will use this ANOV, and then I will use AOV. That means here I'm assigning whatever I'm going to get into AOV. So if I do that, then I say, okay, birth weight, I want to check it or to test it from various categories of mode of delivery. So, or we can choose any, apart from mode of delivery, whatever. What else here is parity? Parity has a lot up to 12. Maybe it might not be that meaningful. Let's see this one. Babies, and then get Jill. Let's see this one. Yeah, I think this 0 here is just by mistake, perhaps. So what we do here is, I'll get back to here. So we get to mode of, I'll stick to the mode of transport, which has a bit some value. So mode of transport, and my data set is called what? Babies. So once I do that, and then I need just to print this one, ANOV, and then I get core analysis of variance, mode, and Bebes, terms, and the like. And then I can summarize the results. Summary, then ANOV. And once I do the summary, to give me a p-value here, for example. So this, and then an F statistics. So since this p-value is huge, that means it's more than 0.05. Remember, if it's less than 0.05, we reject our null hypothesis. But if it's more than 0.05, we fail to reject our null hypothesis. So in this context, we will fail to reject our null hypothesis. What is our null hypothesis in this context? So the null hypothesis in this context is that, I mean, the null hypothesis in this context is that the mean Beth weight for those that were derived using normal derivative, and those that were derived using, for example, Caesarean section, or all these other type of derivatives that are here. So their mean is not that much different. That means it doesn't necessarily matter from which you have the baby has been derived. But here the problem could be that most of the babies were derived using normal derivative. So it might be some issue here in terms of maybe biasness of the data set that we have. So it says that the mean Beth weight for those that were derived using this one is not different from this one, is not different from this one, is not different from that one. So in other way around, the mean Beth weight for normal is equivalent to those for maybe Caesarean section and the like. And then in terms of the alternative hypothesis, so here was alternative hypothesis as well. So for the alternative hypothesis, it will say the mean Beth weight is different in at least one of these. So it might be that the mean Beth weight for this and this is equal, and the mean Beth weight for this one is equal. But if for at least one of these should be different from the other. So that's the alternative hypothesis. Now, here we fail to reject our H naught because the p-value is more than 0.05, and we conclude to say that they are the same. So this is all what I had for today. And next week, I think we'll wrap up. I'll just go through the whole of the lessons that we have had since we started, but in a very fast form, so that I think we have to give room to maybe others that want maybe advanced statistics, but for those that just wanted to appreciate up to this point, and that's good as well. I know people have been coming and going, and there's only one person around now. I don't know if you have any question. If you can hear me, that is. All right. Looks like so that's all we. So that's all we had for today. And thank you so much for the participation. As it has always been, I'll upload this on the Google Drive and then share you so that you can learn on your own and also give unto other people the knowledge that you get from here. So thank you so much and looking forward to next week. So as I said, next week will be the last lesson for today, for this series rather. So next week we will just go through all of the script since like from the introduction. So for those that maybe did not start with us, I will quickly explain through the script of what we did and how we arrived up to where we have arrived now. So looking forward to see you next week and bye everyone.